Hi everyone. So our final project focuses on valvular heart disease as well as mechanical approaches to treatment. So valvular heart disease occurs when there is damage in one or more of the four heart valves, which includes the tricuspid, the pulmonary, the aortic, or the mitral valve, leading to valvular malfunction. And in other words, the disease causes improper closing and opening of the heart valves, resulting in inefficient pumping of blood, with blood leaking back into the chamber, called regurgitation, or pushing against a narrowed, stiffened opening, called stenosis. So the figure on the left displays how a heart valve would look with stenosis versus without it. And we can tell that when the valve is closed, leakage can occur, and when it is open, it's pretty narrowed. Approximately 2.5% of the US population suffers from valvular heart disease, and it specifically accounts for approximately 25,000 deaths in the USA per year, with 61% due to aortic valve disease, 15% due to mitral valve disease, and the remaining 24% due to disease of the other valves. So in order to comprehend how to approach treating valvular heart disease, the understanding of valvular mechanisms is crucial. First off, each leaflet is composed of the fibrosa, the spongiosa, and the ventricularis layer. And the fibrosa allows for endurance of high tensile forces, and it's also the thickest layer of the valve and acts as the main weight bearer. Meanwhile, the ventricularis reduces radial strain while the valve opens and closes. And finally, the spongiosa allows for lubrication during the opening and closing of the leaflets, as well as during pressurization. So the total forces experienced by the heart valves include flexural forces, shear stress, and hemodynamic pressure, as well as tensile forces. And in order to accurately design mechanical replacement valves, it's important to note the transvalvular pressure experienced by each valve as a result of these forces, which are listed on the slide. And thus, remodeling heart valves can be successful when utilizing the correct material, which has proper endurance to the magnitude of forces and stresses experienced by healthy valves in accordance with the values listed above. And overall, the intricate design and engineering of the mechanical valves is crucial, as the features and dynamics of healthy heart valves should be closely replicated for ultimate design efficiency.
One of the most common forms of valvular heart disease is aortic stenosis, which is a type of valvular heart disease where the valve between the lower left heart chamber and the body's main artery is narrowed and doesn't open fully. This reduces or blocks blood flow from the heart to the aorta and to the rest of the body. And this can be caused by the calcification of leaflets, which restricts the leaflet opening over time, and the cusp thickness increases. And the narrowing of these valves causes the velocity of the blood flow to increase as well, where it can sometimes exceed 4 meters per second when the normal velocity of blood flow is 1.35 meters per second. And the severity of aortic stenosis only gets worse over time. And another way that this can occur is through bicuspid aortic valve, which is where the heart valve has two cusps instead of three. And on the right there, you can see an image of how that looks. And so it has an oval-shaped ring instead of a circular-shaped ring for its geometry. And the difference in geometry affects the shear force the valve undergoes. The oval-shaped ring geometry causes there to be high-frequency, unsteady shear force on the valve, and this can lead to early calcification on the valve. And this will eventually result in valve failure. And comparatively to normal heart valves, typically they're presented in an optimized structure and geometry, which allows for the shear stress resistance to be minimized while still maximizing the blood flow. And these sides are subjected to oscillatory shear stress, while the ventricular surface of aortic cusps undergo unidirectional shear stress. And because of this, it's so important that these valves are shaped this way. And so it's important to look at the treatments for this.
Hi, now I'm going to go over some of the current treatment options for vascular heart disease. So in mild cases, the go-to is a medical cocktail consisting of diuretics, blood thinners, and antiarrhythmics. In more complicated cases, which is usually the case, the two options are a valve repair, which is an open heart surgery, or a valve replacement. In the case of a valve repair, two common procedures are the balloon valvuloplasty. So this is when you have stenosis, or namely a narrow valve, you widen it. And then another popular surgery is the kind of opposite of that. It's when you have a wide valve opening, you narrow it to get rid of that backflow and leakage. In the case that the tissue can't simply be repaired, you'd have to replace it with a prosthetic. And so the different prosthetics you can replace it with are either mechanical, biological, or tissue engineered. Mechanical prosthetics are just made of a biomaterial, usually elastomers like rubber. And the main benefit of that is they allow for a lot of control because you can choose the geometry, the shape, the different moduli of the material, toxicity, etc. Biological prosthetics is just using biological material, usually animal tissue, and it does afford you less control than mechanical biomaterial prosthetics. And then a new approach is tissue engineered prosthetics, which is just seeding autologous cells onto a biodegradable scaffold, letting it mature, and then implanting that into the patient. And so since the cells are from the patient themselves, there won't be any danger of toxicity or lack of biocompatibility. And so some considerations and challenges are, they all revolve around how complex and dynamic the mechanical system of the heart is. There's numerous stresses, strains, pressures, and so you kind of need to control for all of these. And so the preeminent material goals are to have high biocompatibility, decrease shear stress. This is really important because shear stress causes valve deterioration and blood clots. You want your prosthetic to be durable, to last a long time, and for it to be porous so that it can allow for blood flow. And so a lot of the research goes into illuminating the relationships between this landscape and all these biomechanical phenomena. So there are three different kinds of modeling. We have in silico, ex vivo, and in vivo. In silico, as you can see in the top right, is mainly just computer simulations to clearly understand the variables at play, like shear stress. Ex vivo is modeling anatomical and physiological systems with physical stand-ins. So as you can see here, they would replace a heart with, a linear piston. And so the challenge with this is that physical models don't really capture all the nuances of, the heart and all the physiology. And then last modeling technique is in vivo, which is just using large animals as a model. So they would get some model animal whose heart system is similar, and then they would perform different surgeries and experimentation on it and kind of see how that translates to humans. And so the future of valvular heart disease and the solutions are very promising. Right now, the efforts are just going into understanding biomechanical phenomenon. Once this improves, then it'll be able to inform surgical technique better. It'll improve device design. And so, yeah, once again, it's very promising, but we do need to understand that as all of these developments are being made, we need to make sure that they are affordable and economic, just because of how prevalent valvular heart disease is in developing nations. And we need to make sure that there's not a socioeconomic barrier to access. But yeah, really interesting topic, very interdisciplinary and impactful area. And so if it sounds interesting, you should probably look into it. And that's the end of our presentation. Thank you for listening.